Good afternoon, everyone. On the East Coast, good morning out west. This is Steve Baxter. I'm the Climate Services Program Manager. I'll be kind of emceeing this month's Climate Services webinar. We're really excited today to have Michael Tippett with us. Mike's done a lot of really cool work across the spectrum in terms of topics of interest to us in climate services, from subseasonal to seasonal prediction, predictability of not just temperature and precipitation, but also things like we're going to talk about today, severe weather, which is something that's kind of on the cutting edge of how we take what we know about the climate system and apply it to really impactful extreme events potentially. Michael Tippett is an associate professor of the Department of Applied Physics and Applied Mathematics at Columbia University. Mike's climate research includes detection, attribution of climate change in models and observations, decadal prediction of Atlantic sea surface temperatures, and seasonal forecasts of the Niño-Southern Oscillation, or ENSO, as well as seasonal outlooks for temperature and precipitation. On shorter timescales, Tippett investigates how severe thunderstorms, those resulting in tornadoes, large hail, or damaging wind, and tropical cyclones are related to climate, both now and in the future. Mike received BS degrees in electrical engineering and mathematics from North Carolina State University, and his MS and PhD in mathematics from New York University's Courant Institute. So Mike, we're really happy that you were able to join us today. I'm glad we were able to get this on the schedule. I think this is going to be a really exciting and informative webinar for our staff, both across the weather and climate services sectors throughout the Weather Service. So we're looking forward to recording this and getting this out to as many of our folks here in the agency as possible. So Mike, whenever you're ready, we're looking forward to your webinar.
Okay, can you hear me?
Yep, loud and clear.
Because you have to say that. Well, I'm feeling a lot of pressure after that introduction. So I'm going to talk about SOS predictability and prediction of severe weather, and this is probably a Coles to Newcastle situation where I am talking to the experts, just to make sure our terms are well defined. When I say severe weather, I mean a U.S. defines severe thunderstorm, so that's a thunderstorm that results in a tornado, 1 inch or greater hail, or 50-knot winds. I'm going to focus on tornadoes for a couple of reasons. One is the data is good. Two, everybody likes tornadoes if they're far enough away. And we all know that there has been a movie about tornado chasing, but not about hail or straight line winds. SOS is subseasonal to seasonal, or seasonal to subseasonal, or something like that. I've included here week 2, which is not really subseasonal. It's closer to the weather aspect. So we have increasing lead times and increasing averaging windows. Most of the prediction I'm going to talk about is the academic kind. So there are 2 kinds of prediction. The hard kind is prediction about the future. This is mostly hindcasts. Predictability. Why do we need to talk about predictability just through the predictions? Well, particularly for this problem, severe weather, the predictable signals are pretty modest. Otherwise, it would be an easy problem, and the noise is large. So by using models, we can leverage ensembles, multiple initializations to get a better estimate of the signal and noise and to make more reliable estimates of the probability shifts. Okay, so in case you're not sure you want to stick around to the end, here are the take-home points. I'm going to talk a little bit about some topics that are different from the usual S2S prediction, right? So if you're thinking about predictions of near surface temperature or precipitation, usually talking about the verifying observations is maybe one line on a slide. I'm going to talk about the observations a lot because probably the most important observations for severe weather are storm reports, but they're not trivial, and it's easy to use them in ways that can cause you problems, not just with reviewer number 2. The other issue, which is a different one also from near surface temperature and precipitation forecasts, is that you would like to use the output of numerical weather prediction models for guidance, but models do not, particularly for the SOS timescale, do not resolve severe thunderstorms. So you cannot use model output directly for guidance. And so severe weather indices, which are functions of the environment, have been developed. and they provide some indication of whether the conditions are favorable for severe weather. The take-home message is that there are many different indices, but basically they need to contain something like CAPE and something like vertical wind shear. So those are the things that differ from the usual SOS activities. Then I'd like to talk a little bit about what I have decided is the state of the art in SOS prediction of severe weather. So I'm going to start from week 1 just to show that this index method works, move out to week 2 averages, monthly, 2-month, and seasonal. It is a good idea to ask ourselves what the sources of predictability are. And for subseasonal, the MJO is always an important candidate. For seasonal, the biggest player is ENSO, and I'll show results in observations and in models that are more evidence to support that, both for severe weather and other things. And some newer work is asking whether the Arctic oscillation is another predictable signal that has an impact on severe weather. Okay, I continue to talk into the void, which even after 2 years feels weird. Storm reports, take them seriously, but not literally. What do I mean by that? The US storm report record is great. No other country has such good data. Goes back to the 1950s, 1950 for tornado, 55 for wind and hail. Lots and lots of information, path length, location, width. The intensities are based on damage surveys. There's additional information sometimes about losses and fatalities. We need those reports because if you look at the weather station network, it's really too sparse considering the size of tornadoes. This map here is showing the weather station network, and it looks pretty dense, but severe thunderstorms are small and they don't last very long. There are other sources of information. Certainly satellites see things that are related to severe thunderstorms. I'm thinking overshooting cloud tops. Radar gives information. There's radar-derived information that's useful. But in some sense, the gold standard are the reports. So that's the good news. There must be, okay, and we can get lots of information from the reports. We can learn when do tornadoes, again, I'm focusing on tornadoes, when do they occur in the US? What's the seasonal cycle? Even if we can't make forecasts, at least we should know what the climatology is. You know, where tornadoes occur. We know how this year is going, right? We can go to the SPC and look at these preliminary reports. We can see that the year got off to a slowish start. The red line is what happened. The dark line is the average over, I guess, the last 10-year period. So a slow start picked up mid-March through mid-April and pretty close to average at this point. Okay, so I said there was good news, there must be bad news. They are reports. So reports always have the problem that if no one sees it, it's not reported, which means that population and where people are has an impact. It's also been changing technology. The rollout of Doppler radar in the 80s and 90s certainly had an impact. Intensity ratings are damage-based. They're not based on measurements of wind speed, so they depend on what the tornado hits. And there have been changes also in the rating procedure at a couple times. It's important to remember that prior to the 70s, they were rated by students from newspapers, so that can't have been great. Last point is the people who collect the reports are the same people who make the forecasts. So these factors probably introduce some non-meteorological factors into the storm data. I'll illustrate a few. Annual numbers of tornado reports by intensity. So EF0 plus means all the tornadoes. EF1 plus means all the ones rated EF1 and greater, and so on. Let's look at a couple of these individually. So I look at EF0 plus, all tornadoes, and I see this huge trend upward. Probably not real. Probably they were getting the hang of things here and had quite figured it out. Maybe after 1990, it settles down. I look at EF2+. So these are, fairly strong tornadoes, and I see this big shift around the mid-70s, and I ask myself, was there a big shift downward in the numbers per year, or was that because the intensity was no longer rated by students reading newspapers, which happened in the mid-70s? I look at EF1+, and I feel good because at least I don't see big changes except for these first few years there. And this is often a quantity that's used in climate studies. If we're looking at S2S, maybe we're only looking at maybe late 90s through present. So some of these issues with trends in the data are less of a factor. Reporting practices can vary by location. What am I saying here? These are all the hail reports. So before I showed you all the tornado reports, these are all the hail reports. This is kind of interesting, right? The hail respects some state boundaries and some other kind of boundaries. So, I mean, if we were doing this in person, I'm sure you would raise your hand and tell me that there are boundaries that match these. That's interesting. What if you look even closer? So the black dots are hail greater than 3/4 inch reports. The blue shading is population and the red lines are roads. Clearly, hail reports are attracted to roads, maybe not hail, but hail reports. And as we've gone from an early period up to 1979, a later period, and so on, you notice this big increase in kind of an east-west gradient of hail. And the question might be whether or not that corresponds to a real climatological gradient or if it reflects the population gradient as well. This is a road to, I think it's I-40 to Oklahoma City and then west to Albuquerque, New Mexico. Okay, so something kind of has to be done with reports to make them useful. A very straightforward thing is to smooth them. This is a Gaussian kernel smoother. So you start off with reports, which are dots, and you smooth them, and you may smooth them more or less. Here are some more dots that get turned into little blobs. And often this quantity might be something that you use as your verification. Victor Gensini and others have put together a nice data set of what they call practically perfect hindcasts. And they have all three categories: tornado, wind, and hail climatologies, tornado, hail, and wind. Okay, so that was the first thing that's different than your usual S2S prediction problem. You have to worry about what it is you're predicting and how you're going to use that in your verification. Next difference is guidance, right? So if you're looking for model guidance, you simply can't say, I'm going to use the model's precipitation to forecast precipitation, or the model's 2-meter temperature to predict 2-meter temperature. When you go to thunderstorms, it's because the model does not have a variable called thunderstorm report. Instead, what people have done for quite a few years now is to create, to look at the ingredients for thunderstorms. You need some sort of instability, and as well as vertical wind shear is also a favorable factor. So you take a couple of favorable factors like CAPE, vertical wind shear, different ways of measuring that, different ways of computing CAPE. You combine those into some index or parameter, and that gives you a way to both interpret observations. So these quantities are used by forecasters even at the warning watch timescale, and to look at the output of numerical weather prediction models. I'm mentioning two here that I will talk about later. One is the supercell composite parameter, and you see it has three factors. The first is most unstable CAPE. Second one is storm relative helicity, and the third one is bulk wind shear. So it looks like I'm giving more, or looks like this parameter is giving more weight to the wind factor because the wind factor appears twice compared to CAPE, and it's multiplicative. Here's another one. This is the Tornado Environment Index, which you will not find at SPC because it's a more recent one and it's designed for climate applications. And what you notice there is that it has this exponential of a log. So that means it's also multiplicative. And it has some numbers that multiply the convective precipitation, which is playing the role of instability, and a number that's multiplying storm relative velocity. And this number is bigger. So this index also gives more weight to the wind component of the index. So the utility of these types of indices is that you can compute them from model output and from reanalysis. And I've shown too, there are many. Unfortunately, I would say that when you go to model output, particularly at longer leads, the indices tend to be more like each other than they are like reality, which is often the case. Okay, so what's the justification for these indices? So this is a very nice piece of work from Brooks about 20 years ago, Harold Brooks, the Severe Storms Laboratory. What it's showing, this axis is CAPE. This axis is vertical wind shear of from reanalysis in the proximity of some events, tornado events. What you notice is, yes, as CAPE and wind shear go up, you have more events and more intense events. And what Brooks calculated was a discriminating line where if you're on one side of the line, expect things to happen and not so much on the other side. How does this justify those previous indices? Well, it's a log scale. And this is a line. A line like this on a log scale, you get by a product. So definitely a product of CAPE and wind is a good discriminator. Second, look at the range on the two axes, right? CAPE goes 1, 2, 3, 4, 5 orders of magnitude, and shear just 3. So what that means is, since this slope of this line is kind of -1 like, for the same amount of change on the line or across the line this way, you need twice as much of a change in percent of CAPE than you do for wind. So this is another indication that severe thunderstorms are more sensitive to the wind component in these indices. Okay, so we have reports, we have severe weather indices that we can compute. Let's take a look at them in week 1 just to see, kind of as a sanity check, to see if they can get events that happen during week 1. This is a work led by Victor Gensini, same guy who did the practically perfect hindcast, and that's what he's predicting here. So he's predicting practically perfect tornado and hail area for the CONUS, okay? And how is he making that prediction? He's making that prediction based on guess forecast, 15-day forecast. I think it's version 11. And he did that for 2 years during the March through May period. And what he does is he computes the supercell composite parameter in the forecast and asks how much area is greater than 2. So how much of the map has SCP greater than 2? And that's a basis for a forecast. Now, what am I showing here? These are chiclet charts, which I know and love. I'm not sure everyone knows and loves, but this name comes from Greg Carbon, who's you may know as well. And what are we looking at? What we're looking at is if you take the thing being forecast, which is SCP area greater than 2, that's a number. And you take that number and you find the color and you plot it for each forecast run. So you have a verification time, and you go down here to read the verification time, you have a lead time. Now, since lead is target or verification minus start, these are lines with slope 1. So you plot all of those forecast runs. And when you see a vertical thing like this, what this is saying is that over multiple start times, the forecasts are consistently putting something at this target date. Okay. I think it's a handy way to see a lot of forecasts from multiple start times. And what's shown underneath here are tornado for the red bars and hail for the green ones. And there does seem to be some connection between when the model is saying something will happen and when things actually happen. I think one of the great values of this presentation is if I ask you, when do the models lose the ability to predict events, you will look at this and you'll say about here. Okay, so they might get, this is 4, 6, they might get to day 8, but it's going to be kind of soupy after that. There's not a lot of run-to-run consistency, and it's hard to believe a model if it's not showing run-to-run consistency. That's the same in 2016, same in 2017. So even without doing the die-off curves, you get the impression from that chiclet chart that, yeah, by the end of week 1, not a lot of skill left, whether I'm using a rank correlation measure or whether I'm making probability forecasts based on my ensemble. Occasionally, you might get some forecasts of opportunity where something happens in tornado and hail on a particular day. This is May 18, 19, 2017, and you might be able to go back more than a week and see some indication, but doesn't seem to happen that regularly. And that does correspond to how we understand the predictability of the weather. We don't expect to be able to predict events past week 1. I wanted to show this just for fun. So this is kind of the same thing. So it's also a chiclet chart. It's a different model. It's a different quantity. But again, I think the conclusion is hard to miss that just looking at run-to-run consistency, not even skill, you don't have a lot past week 1. You maybe are getting climatology right because these blue colors mean less active. So more active in spring, less active in summer. But this kind of says that after week 1, you don't have predictability. You need to start looking at averages rather than events. Okay. Activity forecasts. We need to make weekly averages, for instance. Okay, so this is moving to the part of my talk which is describing the state of the art. This is from 2021 from people at CPC. And what are we looking at here? We are looking at March, April, May forecast from GEFS. I do not know which version. It's the one that has this hindcast. What is being predicted? Local storm reports. So tornado, hail, and wind numbers. How is it being predicted? Again, supercell composite parameter is providing the model guidance. What should we focus on here? This is week 1. This is week 2. Lots of red and yellow here, not so much. If you do some smoothing, this is a 5x5 smoothing, much higher skill. So this is smoothing both the forecast and the verifying observations. But still, big drop off in skill at week 2. So that's kind of what we know to expect. There are a couple of ways that the smoothing can be done, and the way, because at some point we have to connect this quantity, this severe weather parameter, with a number of reports that can either be done by linear regression or something based on singular value decomposition. Pretty comparable skill. And again, that skill drops with lead time for the weekly average. So this sounds like perfect guidance for week 2 US hazards. And indeed, in the past, this is from 2019, severe weather appeared on the US Hazards Outlook. It no longer appears on US Hazards Outlook. I don't quite know that story, but it must be a good one. Okay, the MJO. The MJO is always invoked for subseasonal prediction. Relationship status, complicated. So this was first looked at, I think, carefully in 2013. And what was interesting was that there were two nice papers, and the results were not directly comparable because one looked at tornado days and one looked at violent tornado outbreaks, which is looking at these EF2 and greater of a certain number. And the results were not all that compatible. This was saying phase 2 is the one that's going to get you. This was saying, well, it depends what month. I think the status is still complicated. And I think that significance testing may have played a role. And it's fair to say that, one, you start talking about significance testing, it does seem a little academic or pedantic or something that reviewer 2 is going to bring up. But we want to know if our results are specific to that sample or not. So one thing we might do is we might look at this violent tornado day frequency in one period, in another period, in the full period, and it does seem like that relationship is more robust, whereas the other one not so robust. More progress, 2018, led by a current NOAA employee, Corey Baggett, and he made some nice improvements over previous work because he looked at tornado events in two different boxes. One was a box kind of in the plains area, one more to the southeast. Those earlier works put everything together. Also, an important bit of progress was to look at the lead time because we expect that the MJO impact from the Pacific to the continent, the contiguous US, takes some time. So what might matter might be the MJO phase a week or so before. So he looked at the ingredients, how they depend on phase. So we have CAPE, storm relative helicity, their product, CAPE times storm relative helicity squared. So again, more weight for the wind term, and then tornadoes and hail. And there is a sense that certainly there's consistency that we see, low activity kind of propagating with lead time across phases and high activity there. Also some in the southeast. What's interesting is that was done with the OMI, so the OLR MJO index, and those results seem to be sensitive to whether or not you use that index or whether you use the RMM, which maybe is more widely looked at. So I think that means there's still some uncertainty in that relationship status. That new paper last week, so we can hope that this will clarify everything. I have not read the paper yet, but it doesn't seem to be a simple story, but maybe that's the way it is. Okay, monthly forecast. By monthly forecast, I mean on March 1, you make a forecast for March, April 1, you make a forecast for April, and so on. That can be done using these indices, and it can be done using CFS V2, and you can look at how well it does, for instance, tornadoes. So use the TEI for guidance and ask, am I getting the number of tornadoes right? And do aggregation over these regions. There's some indication that you have, some skill, particularly in times and places when things are going on. I think a valid question is whether this monthly forecast skill is front-loaded. Is it all coming from week 1 and week 2? Is there anything left over for week 3, 4? Same kind of behavior for hail events as well. Okay, more state-of-the-art science here. 2-month forecast. So which 2 months? March, April, April, May. So what's done is you take initializations from February and you look at targets March, April. Initializations from April, you look at April, May. This is going to be CFS-V2 again, and it's going to use the hindcast. The hindcast has pentad frequency, which means you have starts every 5 days. So maybe during a month you have about 5. And for the long runs, you have at least 4 per day. 4 times 5 gives you a 20-member ensemble. Okay. 2-month forecast. Months are March, April, April, May. We're looking at RPSS as the skill metric. What are the predictors? The predictors, this is dynamical statistical in the sense that it's not the grid point values that determine the forecast at a particular location. It's the first 2 EOFs of CAPE and wind jointly together. And if you look at those first 2 EOFs, one is kind of like the amplitude, and the other one is kind of a dipole that goes from northwest to southeast. What's being predicted are the big tornadoes, EF2 and greater numbers. Like I said here, this is RBSS. The colors are without cross-validation, and the dots, which you can see, the dots are where the values without cross-validation are greater than 0.1, and the scores with cross-validation are positive. So this feels like an SAT question. Red without a dark gray dot means negative skill. So the fact that there's red without dots means that when you cross-validate, skill goes down. Sometimes you may think, oh, 0.1 RPSS is very sad. But remember, there's a rule of thumb that says you can convert from either RPSS or Breyer skill score to anomaly correlation with this formula, so that if your anomaly correlation is 0.4, your Breyer skill score RPSS will be about 0.1. So 0.1 is not crazy for this kind of forecast. I don't think I want to go into the weeds, except to mention that it's worth noting these authors also tried to do 3-month targets, and the skill was not as good as the 2-month ones. So there's a question, if there is a predictable signal that persists for 3 months, why doesn't averaging make the skill go up? And if averaging over 3 months doesn't make the skill go up, does that mean the signals aren't persisting 3 months? That question, I think, is relevant because ENSO is persistent. And if ENSO is having an impact, you might ask, well, why doesn't the ENSO impact last for March, April, and May? So does ENSO have an impact? People have been looking at this for quite a while. This is probably the first paper to make a pretty solid case in 2008. And they looked at winter tornado outbreaks. What they find, El Nino, you mostly had gray. Gray means 75% of normal, except for North Carolina and Florida. Florida doing its own thing. La Nina, you had mostly black. Black means higher than average. And again, Florida is doing the opposite. This is work from 5 or 6 years ago. And to get a signal in March, April, May, springtime, what was done was threw everything into the into the analysis. Tornado reports, hail reports, and 2 indices. So when I say tornado blend here, that's the first row, so those indices and reports, and we see that for El Nino, you have more brown, brown means less. La Nina, you have more purple, purple means more. That's for tornadoes. Similar story for hail. And again, Florida does the opposite. And the way of thinking about that is, the impact of ENSO on severe thunderstorms is related to shifts in the jet. Severe weather often happens south of the jet, so the southward shift of the jet in El Nino would be seen as being responsible for the increased activity during El Nino. All right. If ENSO has an impact, let's use it to make a forecast. Oh, something else. The signal seems strongest here, right? So what these authors did was they put a box where the signal was strongest, and they asked what's the activity percent of normal in El Nino, neutral, and La Nina, and they got kind of this picture of more activity during La Nina. Reviewer 2 asked, if you put a box after you saw where the signal was, is that cheating? I think the answer is yes. Okay, so if you have an ENSO signal, you can make a forecast. This is the forecast. So look on the left side to start with. So this is the forecast when ONI, being a 3.4, is positive. Positive ONI. I'm seeing a lot of blue here. Blue means, I think I cut off my slide. Blue means less activity, and except for Florida where there's more activity. La Nina conditions, I have shift more probability above, so I have more green here, except for Florida. So if you tell me the ONI value for DJF, I can make a forecast, and the forecast probabilities, 3 categories, are exactly this. And I don't even have to wait for the DJF ONI to be released. I can make a prediction. Over here is a skill, or our skill score. We have some skill for probability above, probability below, less for tornadoes. And as you might expect, if you look at the skill in predicting indices, that tends to be higher. All right. What can a model tell us about the ENSO signal? Why do we need a model? The ENSO signal is not that big, otherwise people would have discovered it sooner. Noise is large. We only have the years that we have. So in those previous plots, I pointed out sample size. And even if you go back to the beginning of the storm reports, you're only getting 10, 12, 13 samples. And if you stick to the reliable part of the record, it's more like 6, 7, 8. Sample size is small. On the other hand, if you go to a model, you have a big sample size. Disadvantage, you don't have real thunderstorms. You just have indices, and whatever problems that the model has, you still have. Let's do it anyway. Predictability in that box. If you take this box and now look at what CFS V2 does. So this axis on all the plots is near 3.4. This axis is the TEI value in the box. What's important here? What's important is black line is a linear fit. May, almost flat. Very little signal in May, a little bit more in April. Good signal in February, March, not so much in April. So maybe this is why including May in your 3-month average is not a great idea. When you're using observations, you don't really have a choice often because you need to pull months together. What does that mean for your probabilities? Let's just look at February, March, where the signals are big. What it's showing is that during La Nina, blue, below category shifts down 15%, normal is still around 33, and above is around 55. So in February, March, you had big shifts away from your climatological probabilities. April and May, not very big. Really, May is kind of a dud for ENSO in a model. We can do that for the whole map. We can see for above median and below median probabilities what the probability shifts are during La Nina. So above median starts to shift upward slightly. Below median during La Nina becomes stronger. And in April, I'm not even showing May anymore, but we do see that April, the signal is weaker than in February and March. This is a paper that's under review and under discussion, and it's the kind of journal where you can make comments. You can either read the comments or you can be reviewer number 2. What about last year? last year, slow start, picked up, slow start. End of the year, about average. I think it was La Nina here, right? So why did I not get above activity in these other months? February was slow, half of March was slow, half of April was slow. What's the problem? 2021, what else was below normal? I had La Nina conditions. I go to the CPC website and I see blue, very La Nina. But I also look on the CPC website that in January and February, I had a strong negative AO, strong positive AO in March, and then back to kind of not much. Could the AO be the culprit? I asked CFSV2, what do you think of the AO connection to this tornado environment index? What it tells me is that, you know, the phase of the AO has an impact that's nearly as big as ENSO, and it can cancel it out. So if I have a positive AO, I have increased activity. And if I have a negative AO, I have decreased activity. So this negative AO, maybe it canceled out the La Nina conditions. I can also ask CFSV2, what do you think about that? It says, one, La Nina goes with negative AO, or El Nino goes with positive AO, it's kind of a wash in those months. If they happen to line up, you get a strong signal. This is sort of my cartoon of that. If you want to have low activity, you need, El Nino, and negative AO. If you want high activity, you need La Nina and positive AO. Why is the mouse here? This is like the reports you read about in the news where they say, this will change your life. And then you read to the end of it, it says, according to a study done in mice. So yes, this is showing that in a model, in mice, the AO is an interesting signal for severe weather. It remains to be seen if it's also as clear in observations. Okay, so back to the summary. Storm reports are not trivial to deal with. If you want to use model output for guidance, if you want to use reanalysis for analysis, you can use severe weather indices, and they're handy and they've proven quite effective. In week one, there's predictability of events. After that, you have to look at time averages, spatial averages, and the latest research is showing skill at all those leads. To know where that skill comes from, we like to look at for sources of predictability. The MGO situation is still, I think, unsettled. ENSO is an important player, but it could be that the reason the ENSO signal doesn't persist over 3 months is that the AO, which varies on a shorter time scale, might have an impact. I didn't say anything about trends. Shameless self-promotion. I have a postdoc position on this topic. You know, young people who would like to apply, encourage them to do so. The new text out for myself and Tim Del Sol. It's on statistical methods so that you too can respond to or be reviewer number 2. Okay, I will stop there. And hope that I have not looked at the chat. I hope it hasn't gone crazy.
Thank you, Mike. This was really, really great. Yeah, in case our listeners didn't figure out, Mike is your reviewer too. So he's going to find all of your statistical oversights, which is awesome. And I really enjoyed this. I hope our audience did as well. As Jenna put in the chat, you know, we want to take questions now at the end. I'm not sure who all can. Okay, we can see them. Organize the panelists as soon as they come in.
No, I can see them.
So if you have any questions, yep. If you have any questions for Mike, now's a good time to ask. We have about 14 or 15 minutes left in our scheduled hour. Of course, we can end when we need to, but please take a moment now to type in your questions for Mike.
Yep, and Mike, we already received 2 during your talk, so I'll just go ahead and ask. The first one comes from Jack Sedemeyer. Is there a link to the GEFS chiclets that you can drop here? He's familiar with the CFS-based version, but not this new one.
I do not know of a routine gas-based chiclet plot. There is still the one that Greg Carbon did for SPC, and I would imagine that it would not be hard to convert that code, but it doesn't exist. I think chiclets are great, not just for severe weather, but also for looking at things like, you know, AO forecasts.
Okay, and then the next question is from Victor Murphy. Can the presenter comment on the below CFS version 2 based SCP product that is prepared by IRI in conjunction with NSEP? SCP.
Okay, I think that's me or Greg or some legacy code. So this is a product which it just takes the usual CFS runs. It computes this supercell composite parameter. And if it's a chiclet one, it has two things. It has chiclets, which show the CONUS value. And then when you click on the chiclet, the little square, you see the map that goes with it. And if the map is in the past, it shows the storm reports as well.
Okay, great, thank you. We're still getting questions in, but please enter your question into the chat box if you have one. The next question is from Eric Drewitz. Since there's a link between AO and NAO, will there be future research incorporating the NAO into this study?
Sure. I think the limitation, and people have tried to do this, but because the signals are modest and because the timescales are short, it's hard to, you can't use, for instance, monthly average. It doesn't make a lot of sense to use monthly averages of the NAO, I think. Yeah, I think it's wide open.
Okay, do we have any other questions? I'm not seeing any more coming in, but I'll give you guys another minute. While we're waiting for some questions, I will put into the chat box the website where hopefully you guys get this. This is the website where we post all of the recorded seminars from the past, and then this one will be posted early next week. And does anyone have any other questions? I'm not seeing any come in right now.
Actually, Jenna, I'll ask a question if that's okay. While we wait for other folks. Yeah, Mike. So actually, you know, it's very engaging. I'm actually sitting here chatting like on the G chat with some other folks that are on the webinar because it's so interesting and such a relevant topic, I think, for us in climate services.
Right. Did you say you were making jokes with other people?
No, we weren't making. Well, yeah, well, a little bit, but good jokes. But no, this was just so motivating, I think, for all of us. And one of the questions that we were kind of kicking around a little bit was, you know, as we do lit review, and you know, we find ourselves often, like you found in a couple cases, kind of trying to compare apples and oranges. And as the paradigm shifts a little bit from storm reports to environmental indices, it can be kind of hard to wrap our heads around where we need to go next, or where we can go next to start to piece some of these things together toward getting a weather to climate kind of a seamless suite of products out there for stakeholders. So I think you've made a pretty kind of a compelling case that there are certainly nuggets to be had here, and you demonstrate this in week one and also showed this out in subseasonal and seasonal time periods with, of course, you know, their requisite caveats. So what would your advice be to us in the Weather Service as we evaluate the science, as we evaluate a lot of the academic work that you and others have produced and contributed to? What would your advice be to us as we start to try to piece these things together and try to move the agency toward a seamless kind of weather to climate paradigm for severe weather risk assessment and prediction? If that made sense.
Sure. I don't know if Jenna mentioned this, but somebody also put in the chat that Victor Gensini does a SCP, some kind of chiclet and stuff on his website. So how can we make this seamless? I think seamless, one way is to use the same tools at different lead times, right? So with the GEFs going out further sometimes on some runs, that's a way to get past, week 2 and week 3, 4. And CFS, certainly, maybe it's not the best tool, or it's the CFS successor, maybe it's not the best tool at short leads, but at longer leads, it probably is a good tool. So using models which are the same, and maybe techniques. So if you think SCP is good at, if you think that's a good parameter, then use it all the leads so you're comparing apples to apples, and do verifications that are consistent. Because it's not only tornado numbers that people end up using, and by different intensities, they use things like tornado days, and it is hard to compare.
No, thanks, Mike. I think that's great. And one of the things that I know you highlighted there with the severe weather being here and then gone tomorrow with respect to the week 2 hazards is that need to be able for us in climate services to engage with the severe program to make sure we're on that same page. Because that's kind of the problem, is that we're kind of speaking different languages sometimes. And if we can get on the same page, like you mentioned, in terms of tools, methodologies, nomenclature, then we're in a position to communicate to stakeholders who will vary, depending on the application. We can communicate a more seamless product suite. So I think that's good. No, thanks for that. Any other questions come in, Jenna?
Yeah, so Matt Rosencrantz says, can research help us identify the right index then?
I don't think I'm allowed to say no, am I? I mean, research can do anything. However, certainly the papers that I have read, which have focused on the time scale of the warning watch process, those forecasters have seen that some indices are better than others. But whether those differences translate once you're looking at model output, course resolution model output at longer leads, it's not so clear. It may be that, like I said, that the indices are more similar to each other than they are to reality.
Okay, great. Well, I don't see any other questions coming in, but thank you so much for giving the webinar today. Steve, did you have any parting thoughts?
I don't, other than I will encourage everyone. So this is going to be recorded. This is being recorded, and it'll be posted on our website. And so I would encourage everyone that's listening here to share this with your office mates or other folks in the agency that you think would be interested, that maybe didn't have a chance to tune in today. I think this is really, really good, and I think I'm excited from a climate services perspective to start to kind of get the wheels turning again and see how we can make some more progress here in the weather service, being able to provide, like I said, kind of this seamless weather to climate toolkit for our users, kind of building on and incorporating all of this great science that Mike's shown us today. So, Mike, again, thank you for your time today. I know coming up to the end of your semester, it's a busy time, and I appreciate this. I know everyone here does as well. So with that, I'll turn it back to you, Jenna, and we'll close it out.
All right, well, thank you so much. Again, I put the link to where we post them. It's our weather.gov/climate services, and it's the seminars underneath resources. So have a good day, everyone. And Mike, thank you again.